Okay, yeah. Hi, everyone. We will begin the last session of Saturday talk. The next speaker is Victor Gorbenko from the EPFL. Today he will discuss on quantum field theory in digital. Please start. Thank you.
Yes, hello everyone. It's a pleasure to take part in this conference. I guess it's Saturday afternoon in Korea already, so I'll try to at least not to go too much over time and overwhelm you with information. Indeed, I'm going to talk about quantum field theory in the de Sitter space. Most of the things that I say they appear in this paper. Also, I'll mention some ongoing work. And also all the technical details and detailed references you can find in the paper. Let me start with a very brief, broad introduction. So there is a brief history of the cosmological evolution of the universe that I have on this picture. So as we know it, the universe is expanding. And there are several periods of the evolution of the universe. The earliest one to which we have access is called inflation. And it's still a conjectured epoch, so we do not know for sure that it has happened, but it is like the dominant cosmological paradigm. And according to this theory of inflation, the universe was expanding exponentially fast. So, okay, so here I have time going this direction. There is like a size of the universe, and the metric approximately has this form. And you see that there is this scale factor, which tells us how the size of the universe changes with time. And during inflation, it is assumed to grow exponentially fast. Okay, on top of it, inflation predicts that there were some quantum fluctuations of whatever quantum fields that were present during inflation. And these quantum fluctuations of the fields, they gave rise to all the structure that we observe in the universe in the form of cosmic microwave background radiation at some somewhat earlier times, and then these quantum fluctuations, they classicalize during this exponential evolution, and then they undergo gravitational collapse in approximately this period of evolution of the universe, help forming dark matter halos, and then galaxies and stars, and all the structure that we see in the universe. So this is a very remarkable prediction of, in fact, of quantum gravity, because this quantum fluctuations, they also include the metric fluctuations, and that's something that we really want to understand better than we do in the present moment. Also, let me mention that currently, the current period of evolution of the universe after the discovery of the positive cosmological constant 20 years ago, it also has the form of the metric that is close to this one, just with a very different expansion parameter, also called the Hubble parameter. Okay, so the metric of exactly this form, it is known as the de Sitter space, and it is going to play the major role in my discussion. And I just want to emphasize that there are in principle two periods of evolution of the universe where this de Sitter space is playing the role. So this also leads us to two kind of big picture views on cosmology that people often refer to global versus local. So to explain what these points of view are, I like to draw the Penrose diagram of the de Sitter space. So this was a cartoon, or if you want, this is some cartoon of the de Sitter space. And this is a Penrose diagram. So here the time goes upwards, and of course, the metric was conformally transformed in a way to fit the entire de Sitter space into a square, but it preserves the causal structure. Okay, in particular, here we have the cosmological horizon. So light on this diagram still goes at 45 degrees, and this is basically the main thing that you need to remember. And each point on this diagram, if we're in four-dimensional space, is a two-dimensional sphere. Okay, and here, if we consider a single observer that lives in the de Sitter space, who moves along, say, this time-like geodesic over here, he is shielded from the rest of the universe by the cosmological horizon. And this shaded region in orange, it's called the static patch, and that's the region which is causally connected to a single observer. So there is a point of view on cosmology where one studies exclusively observables localized to this static patch. That is, they can be measured by a single cosmological observer. And that is kind of appropriate, maybe if you want to think about the current epoch of evolution of the universe, because whatever galaxies and stars that left our static patch, we will never see them again. So maybe it suffices to think only about the local static patch. However, when we think about inflation, or in principle, when we theorize about the de Sitter space, we can also consider observables that, even though they're not seen by any single physical entity, but they are at least calculable if one has access to the entire de Sitter space. And this is what is called the global view on cosmology. In particular, one can consider observables localized on this future space-like boundary of the de Sitter space. And in this talk, we will focus on these global observables. Okay, so for most of the talk, I will not mention physics of this static patch. I just wanted to make it clear. Here is also on my cartoon of the de Sitter space. This is the expanding part of the de Sitter space that I encountered before, mostly relevant for cosmology. This global geodesic completion of the de Sitter space also contains a contracting part. It's not going to play a major role in my discussion. What I will do, I will basically specify some state, if you like, at time equals 0, and then consider properties of the state in the expanding part of the de Sitter space, and more precisely close to this global boundary. And again, the static patch here, it's some small region of this global de Sitter space.
I have a question in
Sure.
your introduction in the previous slide. So here you're talking about the quantum field theory in de Sitter space, which probably you are talking about this inflation time before the 1 second, right? Is it?
Yeah, well, this inflation here is a bit of a motivation. I'm not going to discuss much of phenomenological aspects of inflation, but yes, you're right.
I see. Yeah, but my case, I'm about to ask you about question of the inflation, because here, is it like here quantum field theory, probably you consider like some kind of effective field theory. So during the inflation, is it possible to apply effective field theory, or you won't have to consider like that is really quantum effect important? Should we consider like a string?
Yes. Okay. So mostly, indeed, the assumption is that effective field, that the Hubble scale during inflation, which also sets the scale, energy scale for these quantum fluctuations, it is much lower than Planck scale or whatever string scale, and hence we can apply local effective field theory to make phenomenologically relevant predictions. Okay. That is the working assumption during inflation, so far it is consistent with all the observations. Of course, it's not excluded that some important non-perturbative gravitational effects also play a role during inflation, but I don't think they're well understood. Okay, I thought about them for some time. Other people thought about it, but I'm not. I probably won't mention them in this talk. Indeed, in this talk, we're going to assume that effective field theory is valid during inflation. And moreover, running ahead of myself a little bit, I will say that even for the most part of this talk, we will assume that gravity is decoupled, which is, again, a reasonable assumption, at least in some of the inflationary models, where one can think of it as just some interacting scalar quantum fields on top of a rigid de Sitter space.
Okay,
Does this answer your question?
Yeah, sure. Thank you.
Okay, good. Okay, yeah, let me accelerate a bit. So among global observables, Okay, there is also a distinction that people like to consider two types of observables. One is the wave function of these fields in de Sitter space, where we compute, if you like, the path integral of fields or also metric that we have in de Sitter space with fixed boundary conditions at the future infinity. Okay, this object is very similar to what is often computed in anti-de Sitter space, where we have instead a time-like boundary, and the values of the fields have Dirichlet boundary conditions of this on this boundary. In which case, we compute the partition function of quantum fields or quantum gravity on anti-de Sitter space. So now, again, in inflation at least, it is very natural to consider different type of observables, which is called the cosmological correlators. So these are observables that in particular can be obtained from the wave function by inserting the absolute value squared of the wave function, whatever fields that we want to compute, or operators that are usually just in effect reconstructed of elementary fields, inserted here at the future boundary. Okay, and then we need to path integrate over values of these fields on this future boundary, right? That's this quantum mechanical rule for computing correlation functions or expectation values, also known as expectation values of operators, out of the wave function. So this object has no obvious analog in ADS, right? And the path integral over sources looks kind of strange from CFT point of view if we also think about this partition function in the ADS CFT context. However, these correlators, these are the most natural observables, at least for me in de Sitter space, and this is what we're going to consider in this talk. Okay, so I want you to sort of avoid the conceptual confusion with the wave function, which would be maybe a more natural object if you were coming from some sort of ADS or ADS CFT perspective to this question. And this path integral over sources is sort of an important issue for things like DSCFT, which is the kind of a natural, straightforward generalization of ADS-CFT to the case of de Sitter, especially if gravity is included as one of the dynamical field. One of the sources is the boundary metric, so we kind of need to path integrate over the boundary metric. So we're back to solving some gravitational path integral, which is not clear if it is well defined. So, as I already mentioned, replying to a question, in this talk we will not consider dynamical gravity. And as a necessary step, we just want to understand the basic properties of cosmological correlators of quantum fields, and in particular, just scalar quantum fields. And compared to, say, anti-de Sitter space, even these objects are relatively poorly understood. Okay, so eventually we want to answer these deeper questions about quantum gravity and maybe even non-perturbative effects. But the point of this talk is much more basic questions in the context of cosmology. They remain unanswered, and that's what we're going to focus on this talk. Okay, and then as I already said, that this inflationary correlation functions or cosmological correlation functions more generally, they, at least in some limits, can be approximated just by quantum field theory on rigid de Sitter space. And now, in particular, for this talk, we will focus on one concrete model that captures many interesting features. Okay, and we will consider this Lagrangian of two scalar fields, the field here have phi and the field sigma, coupled through a single cubic coupling. It's G phi squared sigma, and G is going to be assumed small. And we're interested in computing correlation functions of this field phi at very late times, basically at the future boundary of de Sitter space. Okay, that is like schematically depicted here. For example, these phi fields, they can exchange this other sigma field, and there will be some, some correlation functions like this.
I have a question here.
Yes.
So, here, do you need to add some impose boundary condition on this cosmological horizon, or it's not necessary?
No. Okay, as I mentioned, the idea here is that we specify some state at early time, And then in this state, we calculate correlation functions. So now, okay, maybe I should just say that and in the case of quantum field theory without the Nyquist gradient, there is no subtlety with specifying this state. You can basically take your de Sitter space and cut it at basically t equals 0, and analytically continue to Euclidean, in which case it becomes a half sphere. Okay, so that's like, and that is what's called the Bunch-Davis state. That is also equivalent to implementing a natural I epsilon prescription in perturbative Feynman diagram calculations. Okay, so this is what we're going to do. We have a state like a natural. You see, in Minkowski, there is an unambiguous ground state, right, which is Minkowski vacuum. In de Sitter, it's a little bit more subtle, but there is still a very natural state that is called the Bunch-Davis state that we can call the analog of the vacuum state in de Sitter. And this is a state in which we're going to calculate our correlators. And again, in inflation, it is, I know you can call it an assumption or a natural assumption, that this is roughly the state in which the quantum fields are. Okay.
Okay.
That's clear?
Yes. Okay. Thank you.
Good. Okay. And yeah, feel free to interrupt me because I don't mind, skipping some technical details in the end of the talk. I think it's maybe more important that the basic ideas are mediated. Okay. And again, I will just assume that these fields phi, they are light in a sense that they are lighter than d/2 times this Hubble scale, because there are some subtleties with heavy external fields that I can discuss, but okay, maybe not necessary to understand the first round. And the sigma field, it can have any mass, but again, it's maybe clear a little bit of conceptual if you think of it as some heavy field, some heavy resonance that decays into this phi field. Okay, that's the simplest toy model that I want to discuss. Okay, now let me summarize the main results. So we will see that any perturbative calculation of these inflationary correlators can be reduced to a calculation in anti-de Sitter space. This will give a major technical simplification. Okay, and then we will obtain some explicit answers in this example theory and demonstrate important properties that all de Sitter correlators must satisfy as a consequence of symmetry and unitarity. Okay, so this is just a one-sentence summary of what I'm going to do. Now, to explain a bit better, let me take a very quick detour and consider quantum field theory in flat space. Okay, again, we take the same Lagrangian as I had above, but just we now take a flat Minkowski space and we compute a very similar object. We compute a 2-to-2 amplitude of this phi field when they exchange the sigma field. Okay, this is a very basically simple QFT1 exercise. All of you know the answer. We get this where S is the Mandelstam variable. Now, even this simple answer, it contains some interesting subtleties, right? For physical momenta that are restricted to the case that S is bigger than 4m phi squared, and if m sigma is bigger than 2m phi squared, so that this sigma can really decay into phi fields, the amplitude has a pole. Okay, which is not physical because you see this perturbative answer, I mean, it becomes infinite or at least bigger than 1. So this in particular violates unitarity. So this is remedied by resumming the self-energy diagrams, these bubbles of phi field. Okay, this we all know. There's some geometric series, and our amplitude gets promoted to this more complicated object where this sigma is a self-energy, is the bubble diagram that, okay, I think here in 4 dimensions, 3+1 dimensions, it has this form. It's not so important. What is important is that the sigma develops an imaginary part. So now if we look at the analytic structure of the amplitude in the complex S-plane, there is now a cut that starts at 4m phi squared, and the pole that, remember, there was a pole sitting here, it goes off the physical sheet. So this pole, the correct way to draw this pole is that we need to analytically continue behind the cut. Okay, instead the amplitude itself is analytic on the physical sheet. Okay, there is another t-channel cut that I dropped, never mind. Everywhere here the amplitude is analytic. The absolute value of the amplitude is smaller than 1. We can check that this expression still satisfies unitarity. And moreover, the imaginary part of the amplitude is positive. here it develops this imaginary part. It's positive due to unitarity. Okay, so you see this very simple QFT exercise already leads to some interesting properties that we can calculate and study. So now basically the point of my talk is to develop a similar level of understanding for this de Sitter correlators. Okay, to try to, at least in simple examples, derive these kind of properties and then see which of them can be generalized or at least conjectured to be true non-perturbatively, as for example is the case for unitarity in flat space. And okay, analyticity is more subtle, but there are at least some assumptions, some understanding what happens to analyticity. So why is it so complicated in de Sitter? Because you may say, okay, why just do the calculation and be done with it? And let's review how the calculation goes in de Sitter space. So first we study this inner formalism that I mentioned. That's nothing fancy. That's just the statement that, as opposed to computing the amplitude, the natural observable, is to compute the correlation function, as I said. Where here I just spelled out what it means to have a wave function evolved in time, then a set of correlators, and then the brow of the wave function is kind of evolved backwards in time. Okay, so here we have a time-ordered product. We go to interaction picture, and then here we have a time-ordered product of interacting Hamiltonian, and here we have an anti-time-ordered product. Now we just want, because we have perturbative theory, this H contains a small coupling constant, we're going to Taylor expand its exponents and do weak contractions. Okay. Now there are three types of propagators in these weak contractions, between fields over here, and fields from here to here can be connected. That leads to three propagators that are called left-right, right-right, and left-left corresponding. Now, even for this simple exchange diagram over here, the answer, the explicit analytic answer, was not known just until a few years ago. Okay. So why is that? Well, that's because this propagator expressed, for example, in the position space, it is some hypergeometric function. Okay, so this, so you see now I have three diagrams because I have these three types of propagator for this case. Okay. And now there is this hypergeometric function that one needs to integrate over in some way. And these integrals just become messy. So this hypergeometric function depends on the mass of the particle through this parameter nu that's going to play an important role. Nu is related to the mass of the particle in this way. It's very similar expression to what you find in ADS. But the subtlety is that for heavy particles, heavy means bigger than d over 2 Hubble, this parameter nu in my notation is going to be real, which means that this label of hypergeometric function is going to be imaginary. Okay, and this S is the measure of a distance in the de Sitter space. So long story short, the problem is that if this calculation of this Feynman diagram leads to some integrals of a position in the de Sitter space, very similar to Witten diagrams in ADS. But because now these Green's functions, they have some time ordering in them, these integrals, they're very hard to take explicitly. And there isn't a simple Fourier transform that would factorize these integrals, because the simplification in flat space was in momentum space, okay, where these three-level diagrams basically don't need to take any integrals, they're all factorized. But that was due to Poincare symmetry. And here we have a more complicated, in some sense, symmetry group, which is the symmetry of the de Sitter space. And there isn't a simple, as I said, Fourier transform that would preserve the symmetry and that would factorize this integral. Okay, so that is the technical problem. Now, this basically looking at the symmetry group, Prescott recognized that it's the same as the symmetry group of Euclidean ADS space. And this prompts us to see how the calculation went in anti-de Sitter. And situation is actually much better in anti-de Sitter space. I remind you that the metric, say, of Poincare patch of anti-de Sitter space is very similar to the metric of the expanding patch of de Sitter space. So before I was writing down this exponentially growing, I was writing in this form the metric, but I hope you all see that if we bring this metric to the conformal form, then it just becomes this. And then this metric is very similar to ADS metric. Okay, and in fact, they kind of both DS and ADS, they can be embedded in the high dimensional Minkowski space in this form, where the theta is this hyperboloid that is expanding, and Euclidean ADS is this space-like hyperboloid. And moreover, the boundary of DS and Euclidean ADS, they are basically the same geometric set of points. Now, in Euclidean ADS, again, we usually draw this radial direction horizontally, and then this, okay, here I'm Euclidean, but this, what is in Lorentzian ADS is the time-like boundary that we mentioned before, and here we naturally fix, we compute this observable, that is the partition function of fields living on anti-de Sitter space, that is, we compute the path angle with fixed boundary conditions, okay? Good, and now there are many powerful techniques developed for calculations in anti-de Sitter space. And particularly useful for us is the split representation, where the propagator, which in ADS also takes a form of some hypergeometric function that okay, is similar, but that I didn't write down explicitly, but it can be factorized as an integral over two what's called bulk to boundary propagator, denoted by this letter K. And this really, this split representation is really the analog of the Fourier transform that we had in flat space. Like if you look at this expression, it's sort of conceptually very similar to just the Fourier transform of Minkowski propagator. And indeed, it simplifies using this representation, simplifies computing lots of integrals, and say this three-level diagram that keeps appearing in our talk. It has this very concrete expression in ADS space, known for a long time, say in this paper. Now I come to the main, sorry, there is a little bit of a lag between when I move the screen and when it moves for you. Let me fix it. Now, I'm coming to the main, basically technical statement of my talk. That every quantum field theory on the Sitter space is actually equivalent to a field theory on Euclidean anti-de Sitter space with the double field content. Okay, now let me show you this the case of a single scalar field, but it generalizes immediately to any number of fields. We take, just say, this Lagrangian on the Sitter space, a single scalar field with some potential, and instead of it, we consider a theory with two fields, phi plus and phi minus, with this more complicated Lagrangian that I wrote down here that now lives on anti-de Sitter space. Okay, I remind you that this parameter nu that keeps appearing, it's related to the mass, and this phi plus and phi minus, the two independent fields. You see, it's sort of a strange Lagrangian. It has these imaginary interactions, imaginary coupling constants all over the place. Okay, you see there are these eyes, these phases appear here. Moreover, the kinetic terms, not only they are generically, imaginary, but they have opposite sign. So this Lagrangian looks very, very bad from ADS point of view. But it is okay. We just use it as we're not trying to interpret, give it any physical meaning in anti-de Sitter space. We're just using it as a calculational tool. Our observables are really in the Sitter space. But the claim is that we can use this Lagrangian and do all the calculation. Now, let me tell you one more piece of information that is needed to define this theory.
I have one question in that point. So
please,
here you said that there is a lot of I there. So as a Euclidean quantum field theory, you don't expect like the action is bounded below. It's just given action and you just pairing. You don't worry about that it's bounded below or.
Indeed. This, as I said, this action is definitely not bounded from below. So in particular, I'm not going to make any claims that are true non-perturbatively using this action. I really use this action as a generating, functional for Feynman diagrams, perturbative Feynman diagrams. And that is perfectly fine. You see, if you have even a wrong sign kinetic term, you can still proceed, deriving Feynman rules and computing Feynman diagrams using the usual methods. Okay, and moreover, there are known, as maybe I mentioned later in my talk, there are known non-unitary Euclidean conformal field theories, and that also, if you try to invent some action for them, it will probably not be bounded from below, but they they somehow make sense as a set of Euclidean correlation functions. So indeed, this is it's an important point, but this is how you should think about it as a way to generate an efficient procedure for calculating Feynman diagrams, and maybe deriving some of their properties. Okay.
Okay, thank you.
But it's a good question, yes. Now, these fields phi plus and phi minus, you see they have the same mass, but as we mentioned before, we need to, for fields, we need to specify boundary conditions. And here we're going to pick different boundary conditions for the fields in phi plus and phi minus. And also in our case, there are also fields sigma plus and sigma minus, but okay. Everything is analogous for them. Now, there is a range of masses for which both boundary conditions are allowed in unity in anti-de Sitter space. In particular, this is the range of masses. However, generically, we're outside of this range of masses. Still, I mean, I repeat this, we're not trying to interpret it as a sensible theory in ADS case, and as just computing Feynman diagrams, we can pick any boundary conditions for our propagators in this ADS space. Now, there is a similar relation for the wave function, but it does not require field doubling. And as I already said, going from a wave function to correlators is quite complicated. So it is maybe the fact that the similar relation for wave function was known for a long time, but somehow for correlators, it was not obvious that similar expression existed for correlators. And also, you can see this set of papers that worked on closely related techniques. So proof of the statement.
Just to understand your statement, you're saying for wave function also this 4 copies exist or it does not exist? What did you say?
For the wave function, it goes back to work of Maldacena and also Strominger before that, and there is no field doubling. It is just if you want to compute a wave function of a, say, quantum field theory and quantum gravity on the Sitter space, one can rewrite it as a calculation in Euclidean anti-de Sitter space and some non-unitary theory in Euclidean anti-de Sitter space, just with the same number of fields as you had in de Sitter. And for correlators, I had to double the set of fields. Okay, so that's an important distinction.
I see. So all the recent works by Daniel Bowman and Enrico Payer, where they use actually to calculate correlation function, at least in momentum space, they use these wave functions, right? And
that is true.
So you're saying the wave function is not changing, so it should, yeah.
Yes. Okay. So as I said, there is a relation between wave function and correlators, and here I say it's quite complicated. Of course, if we work, say, to leading order in perturbation theory, the relation between wave function and correlators is quite simple, right? Because remember, to go from the wave function to correlators, we kind of take some path integral, right? And say phi, I know, maybe we do 3-point function, okay? Now, if this thing is something like, you know, some phi k phi plus some g phi cube with some, you know, this k2 and k3, some maybe non-local kernels, right? That indeed Bauman and Payer compute. And then if we want to take this path integral to leading order in G, it is quite simple, right? It's just something like, you know, K3 convoluted with, you know, K2 to the -3, okay? Some Feynman diagram like this, where this is a non-local vertex, and these are the propagators, okay? So this is still relatively easy to calculate if you want to go to leading order. And that's basically what they do. They derive properties. Okay, they do many things, but I think in the papers that you are referring to, they first compute this wave function, and then they derive properties of the correlation functions by using, you know, some formula like this. But if you want to go to high orders in perturbation theory, or, you know, ideally make some statement non-perturbatively, then it becomes complicated to evaluate this path integral.
Right. Okay.
That's what I say here. Yeah, quite complicated doesn't mean that you cannot do it, you know, ever. Sometimes you can do it.
Okay.
Oh, excuse me. Could you remind once again what is the phi plus phi minus and the sigma plus sigma minus? Those are all real fields, right? But the what was the plus and minus? Could you remind me?
Yeah, plus and minus is just, you know, annotation. So I define two fields, phi plus and phi minus, which are going to run into my, you know, propagators and whatever. And this is the Lagrangian, so it defines, you know, the dynamics of this phi plus and phi minus, but also we need to specify boundary conditions, because in ADS space, you know, the theory becomes well defined if boundary conditions are specified. And here I specify the boundary condition. There are two for each field, for each, say, scalar field. There are two possible asymptotics that I write here. And for phi plus, I pick this asymptotic. For phi minus, I pick this asymptotic. Okay, that will define, at least in perturbation theory, the rules for evaluating the diagrams, say the Witten diagrams in this Euclidean ADS theory.
Okay,
Does this
thank you.
answer the question? And for sigma
thank
plus
you.
and
Yes.
sigma minus, okay, we need to write a more Lagrangian that contains both fields. Okay, it's same but a bit more complicated.
So then is it different from the doubling of the field in the informal?
Good question. Let me say, okay, you see, to fully answer your question, I should have shown the proof of this statement, but it's a little bit, you know, it's very straightforward. It goes diagram by diagram using some relations between hypergeometric functions, but okay, it's a little bit long, so I think I would run out of time. Let me just tell you that you see, first you have a doubling due to in, okay? But then also when you have each propagator, say, look at this propagator over here. Each propagator in the zeta space. Okay, so what we do this doubling, and then we do the analytic continuation of all our Feynman integrals by rotating you see, we have a contour like this, okay, in time. Maybe this is eta, my conformal time. So this is the left part of the contour. This is right. You see, this is the in contour, right?
Mm-hmm.
So now we analytically continue it like this. Eta left to e to the minus I pi over 2 z, and eta right to e to the I pi over 2 z. Okay, and then we track how our propagators, these time-ordered, you know, anti-time ordered propagators, get analytically continued. In each of them produces two propagators in anti-de Sitter space. So this leads to yet another doubling of fields. So at this point, we have 4 fields at some intermediate stage. So you see the 4 fields come from doubling due to in, and doubling due to basically trying to reproduce the correct DS propagators from the set of ADS propagators. That's why we need fields with 2 different boundary conditions, basically. You can think of this G nu and G minus nu as 2 fields, basically, well, not yet phi plus and phi minus, but some, you know, prerequisites for phi plus and phi minus, fields with 2 boundary conditions. So then we have 4 fields. And then out of these 4 fields, 2 decouple. Okay, 2 decouple, and then we get 2 fields. So this phi plus and phi minus, there is some mixture of, you know, fields that may be also sometimes called plus and minus in informalism and this extra doubling. Okay.
The in informalism, you have this kind of boundary condition, like is it something like a Schwinger, a Keldysh boundary condition? In the future, like when the left and right meet, there, yeah, you probably. So
it's true. That is, you see, that is somehow, I mean, that's taken into account, because to correctly define these propagators, these 3 propagators, that also I write explicitly here. Sorry, no, I don't. This is the ADS propagator. I had above somewhere these propagators. To define them correctly, you need to think of this boundary condition. That's true.
I see. So under this
Mhm.
analytic continuation, somehow this boundary condition is some incorporated in this kind of
Indeed, it's incorporated in some non-straightforward way, because we land on some Euclidean theory, and in Euclidean theory there is no notion of in, right? So it's true, it gets hidden somehow, but it's preserved.
Okay, thank you very much.
And now basically we use known ADS technology to compute whatever DS correlators we want. So the point here is that once we implement on this rotation, if there is some technique that is known in ADS space to compute some Feynman diagrams or whatever, then we just use it to do calculations in ADS, and that basically gives us an answer. First we compute this three-level diagram, and then as in flat space we have the same problem, that three-level diagram and so on doesn't make sense, violates unitarity and all possible bad things, so we need to resum the bubble. So we resum the bubble, and that produces, after some work, this answer. Okay, so this is the mess, but let me guide you a little bit through this expression. So there is an object here, capital F, that is called a conformal partial wave. So it is some function that is in some dimensions known explicitly, sometimes it's known numerically, but it is completely fixed by kinematics. You see, it doesn't have any dynamics. So some massive function that is known and very extensively studied, especially in the recent conformal bootstrap community. It's something complicated but known, so we kind of forget about it. Okay, then there are all these phase factors that again are important, but do not contain the most crucial dynamical information. The most crucial dynamical information is contained in this object F that we call the spectral amplitude, and this guy has the following form. So you see, first of all, the whole answer is implemented as an integral over nu, okay, to which I will, nu is a spectral parameter, and we'll come back to it later. But this function f of nu, it has this form that is very, very similar to the flat space scattering amplitude. Like if you remember, we had the flat space scattering amplitude, which was something like this: 1 over s minus m sigma squared minus sigma of s, the bubble. So this guy, you see, is very, very similar, and in particular, this b is the bubble in the Citra space. That again can be computed, say, in d equal 2. It has a relatively simple expression in terms of d gamma function. But what's important is that this b, it also has real and imaginary part. Okay, so this f is, I think, is the most direct analog of what we can have as an analog of a scattering amplitude for cosmological correlation. Let's study the properties of this object f. See, here I just duplicate, okay, sorry, here I should put some, maybe I put some f bar, this whole thing here, I call f bar, okay, including the sign factors. So this f bar, it has interesting analytic properties. So first of all, it turns out that I draw on this plot. Okay, so this is a plot of in a variable delta, which is d over 2 plus I nu, and this plot it's for studying analytic properties, same as I had a plot of complex Mandelstam variable for studying analytic properties of the scattering amplitude. So the claim is that, at least in perturbation theory, and okay, we don't have a proof to all orders, but to the orders that we studied, and I would conjecture that it is true at least all orders in perturbation theory, and maybe it's even true non-perturbatively, although because of these issues that our ADS representation, it does not define a good Euclidean path integral, I cannot prove it non-perturbatively. But I think that it's true, that it has the following properties: that this is a metamorphic function, okay, with only simple poles, and moreover, these poles, they are not allowed in this region apart from the real line that goes from d over 2 to d. Okay, so most of the poles are located over here, and they're also allowed to be, if we have light particles in the theory, as we do in our case, then light poles are also allowed to be over here. Okay, so see, that's a little bit surprising. Okay, because when I started doing this calculation, I expected an analytic structure more similar to what we have in flat space, because we have a Lorentzian theory, we have a continuum spectrum, so I was guessing to have some cuts. Instead, there are no cuts. The analytic structure of this object is actually similar to what one finds in anti-de Sitter space. Okay, so it is meromorphic. It is simpler in a sense than in flat space. Now, each of these.
I'm a little bit confused. So had I just restricted myself to just one? So this is after resumming all the loop, right? This is the result after resumming all the loops.
Yeah. This is literally, I'm studying. Okay, so I'm literally showing you the calculation for this resummation of this set of diagrams. And we also checked it in some other examples, for some more complicated theories, and this structure persists. But I invite you to think, at least for a moment, that the structure really holds for all theories. Okay, that's the status.
I see. And suppose by chance I would have just stick to one loop, then I would have got this branch cut structure. You're saying if I resum, then
no, you wouldn't. Even tree level. So even tree level has this structure. The problem with tree level is that at tree level you get a pole right over here, same as in flat space. At tree level you get a pole on the the physical, what you would call a physical value of your parameter. So it kind of, perturbation theory breaks down, unitarity, which I will come in a moment, breaks down. And what resummation does to us, it shifts the pole over here. This distance is, I gamma, which is imaginary part of the bubble diagram. Okay? So that's what resummation does. Very similar to what happens in flat space. It shifts the pole of the physical region, but it doesn't introduce a cut.
Oh, okay.
It's a little bit like if we worked. Are you familiar with, say, rapidity variable in in two-dimensional quantum field theories? People use rapidity variable, and in some cases, like integrable theories, it allows to make the scattering amplitude meromorphic to kind of undo the cut. So it's a little bit like this. What happens here? Somehow in the natural variables in the Sitter space, you get everything meromorphic. You don't get the cut. But this is because maybe it will become a little bit more clear what the physics of this is after I proceed. Ask me again if it's not clear.
So just one more thing, and there is a abstract proof that it will always shift, the pole will always shift to the left, not to the right.
Yes, and this is a consequence of unitarity, because the imaginary part of this bubble is positive.
Imaginary part of the bubble is positive. I see. Is there a this kind of proof also comes from causality? Do you have any causality way of thinking about this thing? Like, if I.
Well, I'll speculate about it in a moment. Okay.
Okay.
And I also have one
Sure.
question. Here, you gave up this unitarity, but somehow here
we didn't get to it yet. Yeah, but it's coming. Okay.
Oh, I see. Okay.
Well, this is one consequence of unitarity, if you like, but I'll make a stronger statement in a second. Okay.
Okay.
So each of these poles, it leads to a power law contribution to what is called the squeeze limits of the correlators. So again, that was a comment in case there were some more, phenomenologists, cosmologists in the audience. But what really this, in a more formal language, that corresponds to operator product expansion of my correlators. So operator product expansion, this is basically performed by pulling the contour of integration into this direction and picking up those poles. So each pole then will give like a contribution of a single conformal primary operator. Okay. And the conjecture here that these poles, or if you like operators, they, in terms of operator product expansion, they correspond to quasi-normal modes of the theory, namely quasi-normal modes of the static patch. So remember, I had this picture with the static patch and the global observables that we study now. But I actually conjecture that when we look at these poles, they correspond to the physics of the single static patch. And I want, again, that's a speculation, okay? Or if you want a cartoon, I want to make it precise, but I don't know how to make it precise. That the reason that there is a convergent operator product expansion for these de Sitter correlators is not because of operator state correspondence, as it is the case in ADS. Like if you remember the proof of operator product expansion in conformal field theories or for ADS correlators, it uses operator state correspondence. And here we don't have operator state correspondence because I think operators appearing in OPE, they correspond to quasi-normal modes, and quasi-normal modes do not correspond to normalizable states. Nevertheless, I think that this convergent operator product expansion exists due to causality. Because you see, if I have to, since you asked this question, I mean, it's going a little bit beyond to what I wanted to say, but since someone asked this question, let me say this. So we do this calculation. This is the future boundary, and say we have, two operators close by. This is time, and these two operators close by, right? That's basically what means to do operator product expansion. I'm computing my diagram in this kind of limit. Okay, and basically the fact that there is a cosmological horizon somewhere here, for that separates these 2 points from these 2 points, it's natural to assume that there is some factorization of the calculation in this limit that basically makes it, some process happening here times the process happening here. And that's like a physical meaning of operator product expansion. And the reason that it converges as good as in conformal field theories, I think is because of causality, okay? But I wasn't able to make it precise. But that's the best answer I can give.
One confusion here, you have dimensions complex, right? But in general, sorry, your these things are on the complex plane, right? Not on the all in the real line, right?
Yes, but that's very natural. I even had this comment here. If we think of them as quasi-normal modes, that's very natural, right? Because quasi-normal modes, they always have the real and imaginary part.
From the quasi-normal mode point of view, it is natural, but from the CFT perspective, it's a little, as you, it's not usual like primary operator kind of thing. These are quasi-normal modes.
I have some comments about it below, but let me maybe before, you're right. It's not a usual CFT, and definitely not a CFT usual in the not a unitary CFT in the usual way. But let me first tell you how unitarity is implemented, okay? That it instead has some nice properties, this CFT.
Right. So just one confusion before that, just one confusion. You said that you cannot make that statement precise that it is these poles are same as the quasi-normal mode pole. In static patch, you can just calculate the quasi-normal modes, right? And then what's the problem in trying to match it with your result?
The problem is that no one has calculated them for interacting theory. For free theory, it all matches, and I kind of refer to this paper for the matching. But also for free theory, sort of everything matches. For interacting theory, no one, to my knowledge, no one has computed quasi-normal modes of a static patch. And if someone did, that will be very interesting to compare. You see, it's a little bit subtle how you even define, well, what is a quasi-normal mode? Because say when we define quasi-normal modes of a black hole, we always have some asymptotic region, and we say, oh, we solve Schrodinger equation, with waves ingoing, outgoing, and do something at infinity. And that makes the problem very well defined. In static patch, it's a bit more subtle because now there is no infinity. So you need to, have slightly adjust your even definition of what you call a quasi-normal mode. And as far as I know, calculation hasn't been done. But yes, we should do it and compare.
I see. Thank you.
I know some people working on it, but I don't think there are final results yet.
Okay.
Okay. Unitarity, I keep circling around it. So to define unitarity, there is another important object, which is the spectral density, which is the imaginary part of what I was calling the spectral amplitude. Okay. And basically, to summarize, unitarity is the positivity of the spectral density. Since I'm running out of time, so let me be brief here. So to derive constraints from unitarity, we interpret the correlator as overlap. And I should say here that unitarity proof does not rely on this Euclidean ADS formulation. Okay, it's very obscure in the Euclidean ADS formulation. And in particular, derivation of unitarity is going to be a non-perturbative statement. We do not rely on perturbation theory when we derive the statement. Okay, I want to distinguish. Remember, my statements about analyticity, they relied on this Euclidean ADS Lagrangian and were perturbative. My statement of unitarity is not relying on perturbation theory or Euclidean ADS Lagrangian. So we interpret our correlator, say the four-point function, as an overlap of two states. So here I have, you know, the bra, right, and the cat, and this is my, you know, here I specify state. Remember, say by doing Bunch-Davis, but it can be any state. Unitarity will hold in any state, but we do here Bunch-Davis, and then we put two operators into the cat and two operators into the bra. So now this overlap of two states, it's a positive definite matrix, but it's so far a little bit useless statement because it's some infinite dimensional matrix. To make it useful, we insert the resolution of the identity between these two states and decompose it into the representations of the conformal group. Then after some, if you want, symmetry allows us to diagonalize this infinite dimensional matrix in a useful way, okay? And the full resolution of the identity, it contains, it is in the cases, okay, modulo some subtleties about some other representations, never mind them. It's going to be an integral over this nu, also known as the principal series, and also sum over, you know, some spin representations. So before I always had the only the scalar contribution because I was considering scalar particle with non-derivative interaction. I didn't have any spinning contributions, but in fact, here we will also have spinning states coming in, and so we will also produce conformal partial waves with spin. These are again known objects, but basically after this generalization, you know, of including the spin, and using this positivity of the norm of the Hilbert space, we arrive to the conclusion that the spectral density for any spin and for any value of the spectral parameter should be non-negative. And now if we just restrict it back to our particular calculation, we recognize in our representation of the spectral factor, and actually maybe it will be a little bit more clear if I put here the integral from 0 to infinity, because remember this rho of nu, it was f of nu plus f of, minus f of minus nu. So the integral that we had before, it gets folded just to the integral from 0 to infinity, and that this spectral density, which was the imaginary or antisymmetric part of the spectral amplitude, it has to be positive. That is the statement of unitarity. Sorry, that's a type. I should just put in of f, which is also known. So we checked this positivity in this G phi square model, and we also checked it at large N and ON model at finite coupling, for example, and it holds. And here I show you just some plots for this rho of nu for this G phi square sigma theory with a small coupling. And you see that if we just take the interacting part, it actually goes negative at some point. Okay. But if we add it together with the free disconnected contribution, it always becomes positive. And here you see this nice resonance peak that is the consequence of this pole over here that is close to the real axis of nu. Okay. Very similar to properties of flat space amplitudes. Okay, how much time do I have? Should I finish in 5 minutes?
It's almost 1 hour, but you can have like 5 or 10 minutes.
Okay, good. Yeah, I'll finish in 5 minutes. But again, I'll answer the question that you know, what are the CFT properties of these correlators? So I claim that it comprises the correlation function of quantum field theory in the citrus space. comprise a Euclidean d-dimensional, say we had d equal 3 for the case of real world CFT. Now our Euclidean ideas formalism demonstrates, at least perturbatively, that there is operator product expansion, even though there is no state operator map. Okay, and each elementary field corresponds to two operators with non-unitary, generically complex anomalous dimensions. Now, CFTs with complex dimensions, they may seem exotic. However, they appear in the description of some condensed matter systems, and actually even description of some models of beyond the standard model physics, like work in Technicolor. They incorporate this complex CFTs. But okay, that is a little bit more exotic. Let me not talk much about this unless someone wants to hear it. Going back to condensed matter, really these complex fixed points are quite ubiquitous. For example, if one takes Potts model in 2 dimensions or a ON model, and there are some theories between 4 and 6 dimensions that this Princeton group studied that actually leads to conformal, well-defined conformal field theories, non-perturbative well-defined conformal field theories with complex anomalous dimensions. There is this theory of deconfined criticality, which is some important class of, again, condensed matter systems. And again, these complex fixed points appear. Roughly speaking, they correspond to weak first-order phase transitions. So if we have a second-order phase transition, that corresponds to a usually a CFT with real anomalous dimensions. If we have a weak first-order phase transitions, roughly speaking, the CFT goes into the complex plane, and that what gives rise to complex anomalous dimensions. I should even say that I didn't write it down, but even if you take the Wilson-Fisher fixed point in 4 minus epsilon dimensions, it has operators with complex anomalous dimensions. That somehow is not maybe very widely known, but it does. Okay.
But those are all unitarity still holds.
No, they also in particular Wilson-Fisher fixed point. Oops. Yeah, Wilson-Fisher fixed point, unless dimension is integer, it is non-unitary. And this series is also non-unitary. And when I talk about the Potts model or ON model, that is about ON model for non-integer n, or Potts model for Potts model is a CFT, or just theory that has a critical point with the permutation symmetry SQ. So you can take Q non-integer, which actually has a non-perturbative lattice definition in terms of some cluster model, where Q is just a number, chemical potential for the number of connected clusters. And for this Q non-integer, the theory becomes non-unitary, and sometimes it also develops complex anomalous dimensions.
I see.
But it's still a well-defined, this Potts model, you can put it on a lattice, and it's for any Q, and it's a well-defined theory.
Okay.
So these things exist, yeah. And as I said, Wilson-Fisher point is probably the least exotic, right? If you, it's a work of Richkov, Hogerworst, and I'm forgetting the third collaborator who showed that it has complex anomalous dimensions for any epsilon non-equal to 0. Okay, this I already mentioned, that operator products expansion can be generated by the contours. Okay, I basically let me skip, basically coming to my conclusions. I wanted to say there are some generalizations, which is basically if we don't include gravity, then the most natural is to, for example, to break the symmetry. At least that's important for inflation, to have a smaller symmetry than the full de Sitter space. People also discuss application of non-perturbative bootstrap that was initiated in this paper, now that we understand the properties of correlators more. And then, of course, eventually we want to add gravity into the game, and maybe I emphasize one point, that the application of our procedure it will lead to a theory with two metrics, which one has alternate boundary conditions. So I think it will have some funny properties, but the procedure we can still continue applying our techniques. And yeah, this is my summary. That okay, basically analytic structure of inflation correlators, they at least in the rigid de Sitter limit, they are somewhat simpler than I expected. They are meromorphic functions. And we derive this unitarity condition, and it will be interesting to understand, say what it would mean in some microscopic sense, because it's not, reflection positivity, which is the usual Euclidean version of unitarity, because that would force anomalous dimensions to be real. While here we have some other notion of unitarity, and like more ambitiously, we would like to maybe, if we want to push this DSCFT correspondence further, apply directly to correlation functions. Maybe we can try to look for some microscopic theories that would satisfy all these above properties. But okay, it's a bit of a speculation whether I do not know how far this can be pushed, but I think it's interesting to explore this direction. Okay, let me stop here.
Thank you very much for the very nice talk. And please ask question.
Okay, I have some naive question. So, is it possible to take a Minkowski limit or flat space-time limit? What I'm saying is that probably in your formulation, you put the size of the de Sitter space or the cosmological constant as a unit, I guess, right? So if
at some point I probably set the Hubble scale to 1, yes.
Right. So if we recover all that size parameter that characterize the DS and take that the cosmological constant to 0 limit, is it first well defined? And if it is well defined, what is happening in you? So is some of the properties seems to be generalization of the usual flat space field theory, but many things are somewhat unexpected to me. So, for example, when you mentioned some complex dimensions of the weakly first order, whether the imaginary part may be decoupling when we take the flat limit to make it some real number or something like that. So,
yeah,
can you make some comments?
I can make some comments, but they are not very deep. So you see, when we consider this, say these 4-point functions, the main problem is that our observables are kind of defined in a way that the external points are very super horizon, right? So there is no simple limit to go to flat space. So what flat space limit exists for objects that are that live in the bulk. For example, if we take this 2-point function, okay, for which we can also write a spectral representation, and it will also contain these contributions with imaginary dimensions. That has a nice flat space limit, because if you take a 2-point function, and this 2-point function is of course encoded in some way in the 4-point function, you just need to undo this propagators, and you get to the 2-point function. Now this guy has a nice flat space limit, and then what happens is that these poles, they collide and produce cuts, and indeed imaginary parts, the fact that these poles have imaginary parts, that will correspond to having some imaginary parts of the amplitudes. So that's what would happen, but we did not work it out in details. Like, we made some checks, some consistency checks, that it happens in some simple cases, but I think it can be done more carefully, yes, and that's what one will see.
Any other question in the online?
I have just one very quick question. So suppose I'm looking at de Sitter 2, they are the CFT one, which is just a simple quantum mechanics. And people do talk about this DFF kind of model, which is, would that be the kind of thing like, so this conjecture that the OP is same as the Cosmo mode, would that be an easy model to check there, or?
I'm not sure if, the CTR2 is the simplest for these purposes, because actually representation theory becomes somewhat messy.
Right.
There are these discrete representations, discrete series all over the place in DS2. The paper I referred to in my talk a couple of times by Penidonis, Varisi, and Hogervorst, they in particular focused on DS2. So I would refer you to their paper for, if you want to see the subtleties, but also the simplifications. There is no spin, which makes it simpler, but instead of spin, you get this discrete series that are a bit of a mess. So yeah, it is. I haven't thought much about the CTR2 in this context.
Just one more. Yeah, sorry. Just one more thing. In your all this calculation you did with the scalar fields, right? The spinning thing will also, the doubling, etc. for one field, those things will also naturally happen for the spinning correlators, for spinning fields also.
Yeah, that's what I would say. Even for me, I guess the most interesting is to consider gravity. For massive spinning fields, it's going to be relatively straightforward. The papers by Slate and Tarona, they work it out for massive spinning fields with arbitrary spin. Now, for things like graviton or gauge boson, it's going to be a bit more subtle. I sort of know what would happen, I think, but the subtlety is that in the gravity case, it's especially clear, because you do this trick and then you have two gravitons, and of course we know that theories with two gravitons, they're not very good. So what will happen is that because of these non-trivial boundary conditions for one of the gravitons, it will get a mass, I think, sort of in the, like happens in some versions of Randall-Sundrum scenario, etc. So for massless spinning fields, there will be subtleties, but I think it will all work in a similar way.
I see. Okay.
Is there any other question? If not, let's thank speaker again.